Week 13, Part 5, Telescopes. So these are all pictures of Goshen College telescopes. We have all of these, and we have even about 3 more besides. But we mostly use the bottom 3 here. But we're going to talk about the general type. The sort of most basic type is this refractor telescope that has a large lens up at this end and then an eyepiece down at the other end, and that's the basic idea. But they all fundamentally work in the same way. The others are all reflecting telescopes. They have mirrors instead of a lens. The large element is a mirror in the bottom of each of these, and even in the back end of this one. But they still work by the same formulas. So let's take a look and see if we can understand how these telescopes work. So here is a diagram of what is called a Keplerian telescope. That's the type that just simply has 2 lenses, a refracting telescope set up in this way. And what I'm showing here are rays coming. Notice that these lines coming in are parallel, as if from something very, very far away, like a star. So this is a red star with rays coming parallel into the lens. It will focus those all to a point about here. This is the focal length of the objective lens. We call this the objective lens. So it focuses us all to a point, but there's nothing there, and so the rays keep on going. And then they enter the eyepiece. And the eyepiece is sitting that same distance away. These 2 share a focal point. Unlike a microscope that has them separated by the tube length, here that would be 0. So because the eyepiece is sitting just at that distance away, then these rays become parallel again and they enter the eye. You notice they enter, though, at a much larger angle than these original rays were. So compared to something that was straight in line with the telescope, this is off by some small angle. So this is like a star that's a little bit off to the side of whatever is the center that you're looking at. And now, looking at it from this direction, whatever these rays seem to be coming from a place that's much further off to the side, off the other direction, so it's upside down, but magnified because that angle is larger. Can we work out what the magnification is? Well, let's see what we can do here. If you look carefully at this figure, I think you can see a line here coming from the center of the lens up to this focal point, and then this other ray that's going back to the center of that lens. And then there's some distance h that these are off of the optical axis, so that's the distance h there. These are those 2 rays. The first ray is coming in at an angle I've called theta objective, or theta of the object. It's the same as the angle out here. That's the angle that these rays are off from the straight direction. So whatever is the angle between the straight on and the star we're looking at, that's theta O here. But now as the rays come into our eye, they're coming at a different angle, and that would be this eye angle, theta sub E. So that's the eye angle. Those are 2 angles. These triangles are not similar, but they are related. They share a side here, this side H. And so we can do a little bit of trigonometry with these 2. We can relate the angle theta to H and FO just by a tangent. So the tangent of theta O is equal to H over FO. I think you would all agree with that. What you might not agree with is this first statement. Theta O equals the tangent of theta. If you work in radians, this is true if the angles are also small. And in a telescope, we assume all of these angles are very small. So that becomes approximately true. The same thing would be true over on the eye side of things, that once again, we'll assume the angle is small, and if this relationship is true, certainly the tangent of theta sub I is equal to H over F sub I. So trying to get the magnification of this, we're trying to see how different is the eye angle than the object angle. How much has that changed? So if we get the ratio of those two, the eye angle divided by the object angle, that would be our magnification. And given that each of these is equal to h over an f, and here is h over the other f, then the ratio of the thetas is going to be like the ratio of the f's, except the other way. Notice the o's and I and e's are switched here. That's because these are in the denominator. So if you do the little bit of algebra there, you'll quickly show that. I've also introduced a minus sign, and I just have to state it here. Technically, I guess one could say that the object angle is one way and the eye angle is the other way, and so that's where the minus sign comes from. But I'm just going to stick it in there. It's clear that the image is upside down, and so the formula needs to have that minus sign in there. The magnification must have a minus sign in it. Though in fact, when we actually calculate it, most of the time you will ignore that fact. When you talk about the magnification of a telescope, nobody ever bothers to include that minus sign, much as you don't with microscopes either. When you talk about the magnification factor, you just don't often bother with that minus sign. A couple of other kinds of telescope-like things. The Galilean Telescope. This is how Galileo looked at the stars. He was one of the first to do that. And interestingly, he was using a telescope in which the eyepiece is a negative lens. But it's still placed consistent with what we just did, because it still shares a focal length with the objective lens. Here's the objective lens, and it's got this focal length here. And here's the eyepiece stuck so that this focal length on this side of it is also there. And it still works, and the formula, in fact, is still the same. We go back to that formula. How do I go backwards here? Let me come over here. Go back one slide. Notice it's minus FO over FE. Well, what if FE is negative? What if the eyepiece is a negative lens? Then you're going to get a positive magnification, which is exactly what you have in a Galilean telescope. Notice the angle of these rays coming in. And now the rays that would be hitting your eye are at a larger angle, but on the same side. So it's right side up. So the image is right side up. The problem that makes these things very difficult to use, at least if you try with any degree of magnification at all, the problem is that these rays aren't going to hit your eye. Put your eye over here and they're going to miss entirely. And what you end up with in a Galilean telescope is a very narrow field of view. You can only see a very small region of the sky at a time. So they're kind of inefficient that way. They have a few other advantages. The right side up, that's a huge advantage. And they're shorter. Since this thing is folded over, you end up with a shorter instrument. For low magnification, these still make some sense, and opera glasses are sometimes made this way. Or little kids' binoculars that are very, very cheap can sometimes be made that way. Proper binoculars, though, that have higher magnification and are well made, have a different solution to the problem of things being upside down. They use a set of prisms in here to reflect the image and turn it right side up. They actually go through 4 reflections inside here, and they turn the image right side up. In the process, they also fold the path around, so the whole instrument ends up a little bit shorter. And there's an offset. Your eyes are sitting here, but the objective lenses are out here, which means they can be quite large and not run into each other. You can have 2 large objective lenses and have them separated by enough that they don't run into each other. And that's useful because in telescopes in general, what matters is not usually so much the magnification. You can get whatever magnification you want just by choosing the right set of lenses. But what you really need is to collect enough light that magnification is useful. We'll see that in just a minute here. Here is another kind of telescope that Newton is the first one to have made this type. in which instead of having a lens as the objective, it's a large mirror. It's a concave mirror. It functions just like a lens. It behaves exactly like what we just saw. It just folds the path back in the same direction again. And then because you can't stick your head here to look at it, you'd be blocking all of the light. A tiny little mirror is put in here to reflect it out the side. And that's where you put your eyepiece and you look in the side. These are excellent telescopes. This is a really good arrangement for viewing the skies. It isn't a good arrangement for looking at anything on the ground because the image is turned around in an odd way. You can't get it to be right side up in any easy way at all. You would be forced into some extremely awkward positions to try to look through it and see it right side up. And so this design is not used for terrestrial observations, but it's used in astronomy because you don't care what's up in astronomy. All right, now let's do an example. Stop this and switch cameras. So one of our Goshen College telescopes, the refractor, in fact, has an objective lens with a focal length of 1,200 meters, 1,200 millimeters. With telescopes, unlike microscopes, you generally swap objective lenses in order to change the magnification. And in a telescope, you change eyepieces. The reason for that is that in a telescope, the objective lens is huge, and it wouldn't be easy or make any sense to be swapping objective lenses. That's most of the price of the telescope is in the objective lens. So instead you swap eyepieces in and out. And so you get a whole set of eyepieces usually, which has choices of different focal lengths. So here are the ones that we happen to have. We've got actually several more, but these are the ones I'm including. These are each listed in the focal length is listed in millimeters. So 6 millimeters, 10 millimeters, all the way up to 40 millimeters. So what's the lowest and what's the highest and what's the 20 millimeters? What would these give us in terms of magnification? So remember, the magnification of a telescope is minus f of the objective divided by f of the eyepiece. So you put in the 1200 and then you divide by an eyepiece, and it's pretty quick to see, well, to get the lowest magnification possible, you'd want the biggest number here. It works kind of opposite. The large numbers on the eyepieces give you the smallest magnification. And we could keep the minus sign in here, I suppose, if we want. 1200 divided by 40 is 30, so this would be a magnification of 30. What about the 20 millimeter eyepiece? 1200 divided by 20, that's going to give us a magnification of 60. And what's the highest magnification? That would come from our 6 down here, and that would be 1200 divided by 6. That would give us a magnification of 200. That's by no means the limit. I've got shorter eyepieces yet. I think I've got a 4. And you can also put in some extra little pieces between the telescope and the eyepiece that serve as a multiplying factor. They're called a Barlow lens that you can put in and give another factor if you want. And I've got Barlows of 2 and 3, I think. So if we went with the 4, 1200 divided by 4, that would give us 300. And then if you want to put the times 3 Barlow in there, you'll get a magnification of 900. That probably isn't useful. When you go to buy a telescope, especially if you buy a cheap one in a store like Walmart or something where they've got them sitting up at the front, they always proudly proclaim in huge numbers the maximum magnification that they'll give you, and that's not a very useful number. By swapping eyepieces in and out, you can get whatever magnification you want. But the question is, what magnification is useful? And that depends on the size of the lens, the diameter of the lens. which is why at the beginning when you saw all those different telescopes that I was showing you there, that I listed them by the diameter of, let's see if I can get back to it here. Oops, there it was. That went too far. There we are. Each of these is listed by its diameter. So the refractor we have has a 6-inch diameter lens in it. The Skywatcher, that's a Newtonian reflector, has an 8-inch mirror down in the bottom. We've got a 10-inch mirror in this one, all the way up to a 16-inch diameter mirror in the bottom of this one. And those are the numbers that matter. Then you can put whatever eyepieces you want in these to get different magnifications. But in the 16-inch, you can magnify things further and actually see more detail. In a tiny telescope, if you magnify things more, you won't see more detail. You'll just get a fuzzier image. It's like if you took a picture of something and then just keep blowing it up, eventually you don't see more. The same thing is true in a small telescope.